Dear friends, I am Professor Dgt going to take here another chapter of your book Be Loud Electromagnetics. This chapter is electromagnetic waves, chapter number 6. This is complete chapter is in your syllabus. The first topic of this chapter is electromagnetic waves in non-conducting medium. That is 6.1, which we are going to take it now. Electromagnetic waves in a chapter number 6, 6.1. Plane waves in a non-conducting medium. Now, we have seen that the Maxwell's equations which provide all the information which we obtain from the classical theory of electromagnetic waves. In a 12th standard, you have studied a various experiment, and one of the experiment was Hertz experiment. Through that Hertz experiment, electromagnetic waves was produced. There was a two iron bar, and between these two iron bar, there was a spark gap was kept, and electric current was provided over there. And over this two iron bar, there was a two sphere which was acting like a capacitor, and they were sliding over this one. And that way, the current is passing through the iron bar, and that will produce the magnetic field. And the charge which is going to be stored on a sphere, that way you can produce the electric field. And by making a variation of this electric field and magnetic field, electromagnetic waves was produced through the spark gap between the two iron bar, and that way the Hertz has produced the electromagnetic waves in the laboratory. This experiment, etc., you have studied theoretically. And then the Hertz has classically given some characteristic of this electromagnetic waves. That is, electromagnetic waves is having the same velocity as the velocity of the light, and hence the light is nothing but one kind of electromagnetic waves which are propagating with the velocity of 3 into 10 raised to 8 meter per second. This kind of information was there. Then the electric and magnetic field are oscillating in a plane perpendicular to each other, and they are propagating normal to the direction of propagation. That means this plane constitutes electric and magnetic field, which is nothing but a wave front, and which is propagating normal to the plane of the wave front with the velocity v. So electric field and magnetic field are perpendicular to each other, and they are perpendicular to the direction of propagation. That means the electromagnetic waves are transferred in a character, and the phase difference between the electric field and magnetic field is going to be zero. That means when the electric field is going to be increasing in one direction, the magnetic field is also increasing in the same perpendicular to that, but at the same time, and both achieves the maximum amplitude at the same time, and they start reducing their magnitude, and they becomes zero magnitude at the same time, and they will reverse their directions on their own axis, and they achieve the maximum in opposite directions. Again they reduce in the same direction. That means the phase difference between the electric field and magnetic field is going to be zero, and that's why it is called a, you know that there are two type of the waves, which is inductive component and radiative component. That means they are having a radiative component characteristic at a large distance. So this kind of characteristics, which was actually you have studied classical theory of electromagnetic waves, which can be proved by Maxwell's equation. Maxwell has derived all these properties mathematically from its Maxwell's equation, and that we are going to study over here now. So in this chapter, in this particular topic, plane waves in a non-conducting medium, we are starting with the Maxwell's equation. So we have seen that Maxwell's equation provides us with all the information that can be drawn from classical theory of electric and magnetic field. We shall show in this chapter that field generated by the moving charge can leave the source and travel through the space in the form of waves. That means in some region of the space, if there are charges are there continuously, and non-uniformly distributed into that volume. And if the charges are moving, that means they will constitute the currents also. And that current is going to be time varying current is going to be there. So they will produce a time varying magnetic field, and the moving charge which is also having a time varying electric field. That means electric field and magnetic field waves are going to be generated from this source, and they will travel into the space or in a medium with the velocity of v, that we are going to prove over here. That is important features of the Maxwell's equation that we are going to derive from this Maxwell's equation. We are starting with the equation number 3. What is the equation number 3? From the Faraday's law of induction, curl of E is equal to minus del B upon del T. That means the electric field is going to be generated by time varying magnetic field. If we consider that these electromagnetic waves are propagating in a linear medium, that means mu, epsilon and sigma are constant. Mu is the permittivity of the medium, epsilon is the permittivity of the medium, mu is the permeability of the medium, and sigma is the conductivity of the medium. And for the linear medium, we can consider that they are going to be constant. Then we can take the curl on one side of equation 3. That means curl of E is equal to minus curl of, that is del cross minus del B upon del T. So time varying magnetic field can generate a electric field, time varying electric field. So that is the physical interpretation of Faraday's law of induction. Now here we will be utilizing simple mathematics, that is A cross B cross C. This is a triple product, vector triple product is there, which can be evaluated by known vector identity A cross B cross C, BAC minus CAB. You know that middle vector comes always with the positive sign, and its coefficient is the dot product of the remaining two vector. Another vector multiplied by the coefficient, that is dot product of the remaining two vector. So this can be identified as del, middle vector is del here. So del into, that means the divergence of del dot E, that is the divergence of gradient of divergence of E will be there, that is the first term. Second term minus E into del dot del, and del dot del is nothing but the Laplace operator, that means del square will be there. So the simplification of this del cross E is nothing but the gradient of divergence of E minus del square E. That is the solutions of the left hand side using vector identity. On the right hand side, del B upon del T. What is B is equal to in terms of the magnetic field? B is the magnetic field induction. That is equal to mu H will be there. So if you substitute here mu H, this is nothing but minus del cross mu del T of H will be there. That means differentiation with the magnetic field H will be there, and we can interchange the order of differentiation. Del indicates special differential operator, which is nothing but del x I caret plus del y j caret plus del z k caret. That means it is a differentiation with respect to space coordinate, and del t is a differentiation with respect to time coordinates. We can interchange the order of differentiation, it makes no difference. So we can say that this is equal to minus mu del T of curl of H. And what is the curl of H? From the Maxwell's fourth equations, Ampere's law, which was modified, that is curl of H is equal to current density J plus displacement current density del D upon del T. That can be substituted for this side. So minus mu del T of current density J plus del D upon del T. Del D, capital D is nothing but displacement electric field, and capital D is equal to epsilon E. That means it is converted into the form of the electric field. So this converted into minus mu del T of J is equal to sigma E. Sigma is the conductivity of the medium. That means it is related with the electric field in a medium with the conductivity of the medium, and electric field. So current density J is equal to sigma E, and the displacement electric field D is equal to sigma E. We can substitute and we can simplify this equation. So using the well-known vector identity to transform the left-hand side on equation 4 of 5.56 to transform the right-hand side of the above equation, we get the left-hand side is nothing but the vector triple product. So the gradient of divergence of E minus Laplace operator del square E will be there. That is equal to minus mu del current density J upon del T minus mu epsilon del square E upon del T square, because del D upon del T again it is differentiated with respect to time derivative. So second derivative del square E upon del T square will be there, and D is equal to epsilon E. That's why this variable is converted from D to E, and this becomes mu epsilon. Now gathering this differentiation term of the electric field on the one side, we will get del square E becomes positive. Let us make it positive, or you can bring it this side and it becomes positive. So del square E minus second derivative of the time derivative mu we are putting here. This is also second derivative, but with respect to space coordinate. This is also second derivative of the electric field, but with respect to time coordinate, and this is the first order derivative of the electric field with respect to time coordinate. So del square E minus mu epsilon del square E upon del T square minus sigma mu sigma del E upon del T, that is equal to the gradient of divergence of E, and the value of divergence of E from the Maxwell's first equation we can substitute, that is equal to Gauss's theorem in a differential form, sigma upon epsilon 0 rho upon epsilon 0, where rho is nothing but volume charge density, charge per unit volume. And if you consider that if these electromagnetic waves are propagating in a medium where there is no charge, that means volume charge density sigma is going to be 0, rho is going to be 0. In that case, this term inside the bracket is going to be 0. So divergence of 0 is going to be 0. So on the right hand side, we can substitute in equation 6.1 is going to be 0. That means equation 6.1 converts into this equation 6.2, that is del square E minus mu epsilon del square E upon del T square minus mu sigma del E upon del T, that is equal to 0. So important equations related with the space derivative and time derivative which we of the electric field we obtain for equation 6.2. Now assume that electric field is a time varying electric field, that means it is a function of R and T, and it can be given as a complex quantity. So E is a function of R, that means its amplitude is a function of R, and its phase vector is given by e raised to minus I omega t. So the electric field, which is a function of R and T, can be given as a complex quantity. E is a function of R, e raised to minus omega t, and we can compare the relative magnitude of the third term to the second term of equation 2. That means we take the ratio of modulus of mu sigma del E upon del T to the modulus of mu epsilon del square E upon del T square. That means we have to find out the value of del E upon del T, and we have to obtain the value of del square E upon del T square. So we have to differentiate this electric field. E is a function of R and T is equal to ER, e raised to minus I omega t, with respect to time first derivative and with respect to time with second derivative. We have to obtain. So what is the differentiation of this one? ER is a constant. So e raised to minus I omega t. If you differentiate the first time, you will get minus I omega. That means I omega into ERT will be the differentiation of this one, and I square omega square is the second order differentiation of this one that we can substitute in our equation. So in the numerator, you will get mu sigma into omega upon, in the denominator, mu epsilon into omega square. Now numerator and denominator, mu will be cancelled out and one of the omega in numerator is there and denominator omega square will be there. So omega is going to be cancelled out, remains sigma that is conductivity of the medium, upon epsilon omega. So the ratio of the amplitude or magnitude of the third term to the second term is given by sigma upon epsilon omega. And if you take this sigma into denominator, that means it becomes epsilon upon sigma, and epsilon upon sigma is nothing but the relaxation time, which we have already studied in a previous chapter. So epsilon upon sigma is nothing but relaxation time, and that we have studied in decay of free charges. That means charges is decaying very fast when the switch is going to be open, and that way that can be substituted in this one. So you will get 1 upon omega tau, and omega is equal to 2 pi upon capital T, and T is the period of oscillations. So capital T upon 2 pi tau is the ratio of the third term to the second term of equation 2, and that is given by T upon 2 pi capital T, where we have used replace, that is epsilon upon sigma by the relaxation time 5.59, and omega is equal to 2 pi upon capital T, where T is being the period of oscillation. And if the now we consider that if tau is very small compared to T, which is the case for the conducting medium, that means the value of tau is equal to epsilon upon sigma, and if the value of the sigma is very large, that means epsilon upon sigma is very small, and that means tau is small, and sigma is going to be large. That means conductivity of the medium is very large. That means the medium is very conducting medium is here. So in that case, that tau is very small. So in that case, this ratio T is greater than tau. So this ratio is very high. That means the third term is dominant. This means mu sigma, this term is dominant in this equation compared to the second term. So you can replace these equations by del square E minus mu sigma del E upon del T, that is equal to 0. And this equation is known as the diffusion equation, that is for the conducting medium. So del square E minus mu sigma del E upon del T is equal to 0. That is equation number 6.4, which is known as a diffusion equation, which is the electromagnetic waves are propagating in a conducting medium, that we are going to see in a 6.5 topic of this chapter. Now, if the tau is greater than 0, when it is going to be greater than 0, epsilon upon sigma is very small. Epsilon upon sigma is going to be very small when sigma is very small. That means the medium is non-conducting medium is there. In that case, tau is very large compared to the T. And in that case, the third term can be neglected because medium is a non-conducting medium. Mu sigma term, third term in equation 6.2 is almost neglected compared to the second term, and your equation 6.2 reduced to del square E minus mu epsilon del square E upon del T square is equal to 0. That means we can obtain the electric field second derivative with space coordinates of electric field, and the second derivative of the electric field with respect to time coordinate multiplied by minus mu epsilon, that is going to be 0. So in this forms, mathematical forms, we obtain the electric field. Similar kind of equations can be derived for the magnetic field. That means del square H minus mu epsilon del square H upon del T square minus mu sigma del H upon del T, that is equal to 0. This also we can derive by taking the curl on both the side of the equation 4 of the Maxwell, substituting the other values and doing the simple mathematics, we can obtain the similar equation for the magnetic field. Differentiation with the space coordinate, differentiation with the time coordinate, and differentiation with the time coordinate first order and second order. And for a non-conducting medium, the third term can be neglected again, and you will get del square H minus mu epsilon del square H upon del T square, that is equal to 0. So you will get 6.7 equation, that is a similar type of mathematical forms of the electric field and magnetic field. Del square E minus mu of sigma mu epsilon del square E upon del t square is equal to 0, del square H minus mu epsilon del square H upon del t square is equal to 0. These equations are of the same type of the equation of wave equation we are familiar with, where psi is a function of r and t. Then we can say that del square psi minus 1 upon v square del square psi upon del t square is equal to 0. That is equation number 6.8. These equations are of the type of the wave equation we are familiar with. The general wave equation is del square psi minus 1 upon v square del square psi upon del t square, this is equal to 0. This is the wave equation. And comparing equation 6.5, 6.7 and 6.8, which are of the similar forms. So we can compare them and we can say that 1 upon v square is equal to mu epsilon, and that means the phase velocity v of the electromagnetic waves or phase velocity v of these waves is nothing but given by mu epsilon raised to minus 1 half. And if we convert this medium, which is a linear medium, we have absolutely, if it is in a vacuum, then mu is converted into mu 0 and epsilon is having a value of epsilon 0, which is a known value, and that means the electromagnetic waves can propagate in a vacuum. V is equal to mu 0 epsilon 0 raised to minus 1 half. This is the velocity of light in a vacuum that you know very well. So equation 6.9, that means electromagnetic waves phase velocity mu epsilon raised to minus 1 half for a linear media, and in a vacuum B is equal to mu epsilon 0 mu 0 epsilon 0 raised to minus 1 half. We conclude that any time variation an electric and magnetic field are propagated with the same velocity. So electromagnetic waves, which are time varying electric and magnetic fields, are propagating in a linear media with the phase velocity v is equal to mu epsilon raised to minus 1 half. Now if you consider that electric field and magnetic field are vector quantity, where psi was a scalar quantity. So the equation 6.8 was for the scalar quantity, and equation 6.5 and 6.7 are vector equations, which means that the latter equations are valid for each component of electric and magnetic field, because electric and magnetic field are vector quantities. Now the solutions of the equation 6.5 and 6.7 is nothing but the solutions of wave equations. So simplest type of the wave, that is the solution of 6.5 or 6.7, is a plane wave. That means solutions of this equation is nothing but the plane waves. Plane wave is a specialized concept of a general wave equation. General waves means you can say that a point source and the electromagnetic waves are generated from that point source, and it is propagating in all various directions. And study of this one is slightly difficult because it is complicated. So we take a specialized case that when the point source is going to be there, out of all the directions, we consider that electromagnetic waves are propagating in one particular direction. That is the concept of plane waves. That means the one particular directions the electromagnetic waves are going to be propagating, and normal to that there is a wave front you can assume, which constitute the electric and magnetic field vectors. And this electric and magnetic field vectors at particular wave fronts, that amplitudes remains constant. That means it is not changing, that is constant at every point on that plane. But it is a function of the distance from the source and time from where it is generated. So this is the concept of the plane wave, which is considered to understand the various concepts of electromagnetic theory. The simplest type of the wave, that is the solution of equation 6.5 or 6.7, is a plane wave. The relative simplicity of the plane wave solutions of the Maxwell equation enable some of the important elementary physical characteristics of the electromagnetic field to be evaluated without appeal to the other than quite straightforward mathematics. That means using the straightforward mathematics only, we can find out so many basic elementary physical characteristics of electromagnetic field can be find out, or it can be evolved using the plane wave concept, because plane wave solutions is going to be simple, and then we can generalize to the general waves. Since the plane waves are good approximation to the actual waves in many situations, we shall discuss the plane wave solutions of the above equations. A plane wave is one in which the wave amplitudes, the field vector components, is constant over all points of the plane, normal to the direction of propagation. This plane constitutes a wavefront which advances with the velocity v in the direction to the normal to itself. The field vector components that lies in a given plane are function of perpendicular distance of plane waves from the source and of the time. So, the concept of the plane wave, you have to understand very clearly. What is the concept of the plane? We consider that from a point like source or from any source, the electromagnetic waves are generated, and that electromagnetic waves are propagating in one particular direction, and it is propagating like a wave front. So in every wave front, there is an electric field and magnetic fields will be there, components will be there, and that electric field and magnetic field components are constant over the all points of that plane, but they are function of distance from the origin as well as of the time. This is the concept of plane waves, and this wave front is propagating with the phase velocity v perpendicular to the direction of perpendicular direction to the wave front. This is the concept of plane wave. So very importantly, you understand this plane wave. So plane wave is one in which the wave amplitudes, the field vector components, is a constant over all points of the plane normal to the direction of propagation. This plane constitute a wavefront which advances with the velocity v in the direction normal to itself. The field vector components that lies in a given plane are function of perpendicular distance of the plane from the origin and also of the time. We may choose our coordinate system in such a way that the direction of propagation coincide with, say, x-axis. Since the wave function in this case does not depend upon y and z, the wave equation takes one dimension form such as del square psi upon del x square minus 1 upon v square del square psi upon del t square is equal to 0. So now we will take the concept of a plane wave for a general function, wave function psi. So let us choose our coordinate system such that the direction of propagation of the wave is, say, x-axis. So the wave front will be perpendicular to the x-axis. That means it will be in a yz plane. That means the psi function, which must be the function of x coordinate only. It is independent of y and z, because in a yz plane, the components of the wavefront or electric field vector and magnetic field vectors are going to be constant. So similar way, if we consider that electromagnetic waves are propagating in the x direction, that means electric field will not have a x component. That means Ex component is going to be 0. Similarly, it will not have a magnetic field component. That means Hx component is also going to be 0. So Ex and Hx component of electric and magnetic fields are going to be 0, because they will be lying only perpendicular to this one. That means in a wavefront yz plane only. That means the electric field will be having Ey component and Ez component. Similarly, the magnetic field is also having Ez, Hz and Hy components only. And this components on a particular wave front from a particular distance from the origin and at particular time, it is going to be constant at all points of the wave fronts, but they are a function of a distance of x and t. So the wave function psi, which is now function of x and t. So the general solutions of this psi, which is a function of x and t, can be obtained by integrating this differential equation 2 times. We'll get the psi, which is a function of x and t, is equal to a e raised to I kx minus omega t plus capital B e raised to minus I kx minus omega t, which can be obtained as like this, that f is a function which is a function of x minus vt plus another function g is a function of x plus vt. A and b is a constant of integration, and this constant of integrations are going to be complex complex quantity is going to be there. Here f is a function of x minus t, where v is the phase velocity of the wave. That means electromagnetic waves are propagating in positive x direction also, as well as it is propagating on negative x direction also. So where a and b is the constant of integration, which is generally complex constant, and k is nothing but wave vector, that is equal to omega upon v, where v is the phase velocity of the wave. Equation 6.12 represents the wave traveling to the right and to the left with the velocity v. That means it is propagating in positive x direction as well as in a negative x direction with the phase velocity v. We assume that the plane wave fields are of the form. So we consider that we oriented our system such that the electromagnetic fields are propagating in x direction. That means electric field is a function of x and t, and magnetic field is also a function of x and t. So E is a function of x and t can be obtained as a complex function E0 e raised to I kx minus omega t, and h is also a function of x and t, which is equal to h0 e raised to I kx minus omega t. Because it is propagating in a x direction, electric field will be having only Ey and Ez component, and magnetic field H is also having only Hy and Hz component. So Ey component of this electric field 6.13 is nothing but Ey, which is a function of x and t, is equal to E0y e raised to I kx minus omega t, and Hz or Hy is equal to function of x and t, that is equal to h0y e raised to I kx minus omega t. Similarly, z components will be there. Now, from this equation 6.13 and 6.14, we have seen that phase vectors are going to be the similar one. You consider that z is equal to z0 e raised to I theta, where theta is equal to kx minus omega t for the electric field, and for the magnetic field also theta is equal to kx minus omega t. That means theta 1 and theta 2 are going to be the same. That means the phase difference between the electric field and magnetic field is going to be 0. That means the electric field and magnetic field are oscillating with the same phase. That we have assumed here for the radiative components. You know that. That means electric field and magnetic fields are oscillating in the same phase. How we have taken in these equations? For that, we can give the justification from here. Let us introduce that there is a phase difference between the electric field and magnetic field. They are not oscillating in the same phase, but they are oscillating with slightly phase difference of alpha. So these equations can be represented like this. That means E is equal to E0 e raised to I kx minus omega t, and H is equal to H0 e raised to I kx minus omega t plus alpha. That means theta 1 and theta 2, they have the phase difference of alpha is there. We have introduced the phase difference alpha. We'll find out what should be the value of alpha. One may ask, we find from the equation 6.13 and 6.14 that you have assumed that E and H are to be in phase. Is this correct? Our assumption is correct or not? The justification for this assumption made will be found in the following arguments. If possible, let alpha be the phase difference between E and H. In that case, we can modify our equation. That means E is a function of x and t, that is equal to E0 e raised to I kx minus omega t, and x is a function of x and t, that is equal to H0 e raised to I kx minus omega t plus alpha. the fields E and H has to satisfy the Maxwell's equation. So let us consider the third Maxwell's equation, or Faraday's law of induction. Let us substitute the value of components of the electric field and magnetic field in this Faraday's law of induction. Curl of E is equal to minus del B upon del T. How to evaluate this determinant? We know that A cross B can be determinant by taking a determinant ijk. Second row is nothing but del x, del y, del z, and the third row is the component of the electric field, that is equal to ex, ey, ez. That way, curl of E can be evaluated. Now, in our particular case here, the electric field and magnetic field are propagating in x directions. That means in the direction of propagation, that component of the electric field and magnetic field is going to be 0. So Ex component and Hx component is going to be 0. Bx component is going to be 0. Second thing, for the plane wave solutions, the wavefront is along the yz direction is going to be there. That means on every point on the yz plane, the electric field components and magnetic field components are going to be constant. That means variation of the electric field and magnetic field over a particular wavefront is not going to be permissible. So del y and del z is also going to be 0. So this determinant for del cross E is equal to ijk. Ex component will not be there. So Ex component is going to be placed 0, Ey and Ez components, and the variation of del x is going to be only permitted. So in the third row, only first component del y is going to be there. Del y is going to be 0, del z is going to be 0, and on the right hand side, the magnetic field is also not having a Ex component. So we can say that this is nothing but minus del by upon del t plus z minus k caret del bz upon del t. Now we will find out and simplify this one. We'll get that del Ez upon del x, that is equal to del by upon del t. That means it will be having only j components. So here, by evaluating this determinant, we get minus j into del Ez upon del x, that is equal to minus del by upon del t. Minus j is going to be cancelled. So the scalar equations we obtain del Ez upon del x, that is equal to minus del by upon del t. That is the first equation is going to be there. Second equation is related with the z components, that means k factor. So k into del Ey upon del x, that is equal to minus k into del bz upon del t will be there. Therefore, del y and del z of electric field is going to be 0 since E travels in the x direction. Now, we can substitute that we'll be having, we can utilize the second equation here, del Ey upon del x. So we want to have the Ey component of this equation. So what is Ey component of this equation? Ey is equal to E0, y is the amplitude, e raised to I kx minus omega t, and bz component is equal to bz components is equal to h mu into h. So mu into h0z e raised to I kx minus omega t plus alpha will be there. And if we take and differentiate with respect to x, this first equations, you will get ik into this quantity as it is. So differentiating this one, del Ey upon del x, that is equal to ik E0y e raised to I kx minus omega t. And differentiating magnetic field with respect to time. So mu h0z e raised to I kx minus omega t plus alpha into minus I omega will be there. So that means by removing that minus sign, we'll say that I mu omega h0z e raised to I kx minus omega t will be there. Now, taking the real part of this complex quantity, you know that complex quantity z is equal to z0 e raised to I theta. That means the real part of this one is cos theta plus I sin theta. Cos theta is the real part and I sin theta will be imaginary part. So we'll taking the cost functions only here. So I is going to be cancel out both the sides. So k times E0y cos kx minus omega t is equal to mu omega h0z cos kx minus omega t plus alpha. Now this left hand side and both the right hand side both has to be true for all value of x and t. For the variation of the different value of x is a coordinates and t is also time coordinate. So all x coordinate in a positive x direction as well as in a negative x direction, and for every time from t is equal to 0 to t is equal to infinity, this equation has to be true because it is derived from the Maxwell's third equation, and that is for time varying or a static condition. This equation has to be true. So this equation is only true in case if alpha is to be 0. So if alpha is taken 0, then and then only this equation is going to be true for all value of x and t. That means it indicates that electric field and magnetic field are in a phase. That means they are oscillating in the same phase. So the equation is equal to E0 e raised to I kx minus omega t and H is equal to H0 e raised to I kx minus omega t, because alpha is going to be 0 and they are oscillating in the same phase. And that means whatever classical theory assumptions was there, that means radiative components where electric field and magnetic field are oscillating in the same phase is true, which can be derived in the Maxwell's equation also. This is true for all value of x and t. The only value of alpha which satisfies this condition is 0. Therefore, E and H are to be in phase. Now, let us take the ratio of the electric field to the magnetic field. So, E0y upon E0 H0z, that is going to be taken. Cos theta is going to be same both the sides. So, it will be cancelled out. So, E0y, or that is considered to be the electric field components upon magnetic field components. So, E0 upon H0, that is equal to mu omega upon k will be there. And this is having a dimension of impedance, that is ohms, and hence it is designated as Z0, and this radio Z0 has the dimension of impedance and is called the intrinsic impedance of the medium. So the electromagnetic waves are propagating in a medium where the electric field to the magnetic field, which is having the amplitude ratio, is equal to mu omega upon k, and that is nothing but the characteristic of the medium, and that's why it is called the intrinsic impedance of the medium that is designated. You know that omega upon k is nothing but the wave velocity. So this can be said that mu into v. Mu is the permeability of the medium and v is the phase velocity of electromagnetic waves in a particular medium. So this is the characteristic of the medium, and that is designated as the intrinsic impedance of the medium. Thank you very much, friends.